Mr. Christopher Dhanraj, Senior Engineer Program Manager and Consultant in Semiconductor and Medical Devices, as a guest speaker. We welcome you, sir. Before we begin the proceedings, I invite Dr. S. Krishnaveni, Triple E, to deliver the address.
Okay, no.
Good evening, all and all present here. It gives me immense pleasure to welcome you all for the 46th technical lecture organized by the Institute of Engineers, Tiruvallur Local Center. Today's section promises to be both insightful and inspiring as we delve the fascinating world of semiconducting, manufacturing, processor and testing ecosystem. We are deeply honored to have us the highly accomplished expert in the field, Mr. Christopher Dhanraj, Senior Engineering Program Manager and Consultant in Semiconductors and Medical Devices. With a wealth of experience spanning across the advanced technology domain, Mr. Dhanraj brings with him deep industry knowledge, strategic insight, and practical expertise that will be greatly benefit for all of us today, students, researchers, and professionals alike. Semiconductors are the backbones of today's digital world, powering everything from smartphones to medical devices, from electrical vehicle to AI. The precision, complexity, and the evaluation of semiconductor manufacturing and testing are critical to innovation and product reliability. This seminar, Insight, will surely help us to bring better understanding the challenges, emerging trends, and future opportunities in this domain. On behalf of Dr. Angel Educational Research Institute, I extend a warm welcome to our eminent speaker and express our sincere gratitude for taking the time to share his knowledge with us today. We are excited and eager to learn from you your valuable experience, sir. I also take this opportunity to welcome all the faculty members, industrial professionals, research scholars, and our beloved students who have joined for us for this important lecture. Let us look forward to an engaging, enlightening, and thoughtful, provoking session. Thank you.
Thank you, ma'am, for the warm and inspiring words. To give us an overview about the Institution of Engineers and its initiatives, I invite Dr. M. Ganeshan, ex-officio member, IEI TVLC, to speak a few words. Please, sir.
Good evening, all of you. So I have great pleasure in welcoming Mr. Christopher Dhanraj, sorry. So to our university, so he's visiting our university for the first time. So I'm very happy to invite you, sir. And also I have been given a responsibility of telling about the Institution of Engineers. So today this program is hosted by the Institution of Engineers, Tiruvallur Local Center. So for the information of the students I am telling, so Institution of Engineers, Tiruvallur Local Center, which is functioning at our university. So the Institution of Engineers is conducting number of seminars, workshops, industry visits for the benefit of student community. So this program is also one of that. So I would like to brief about what is Institution of Engineers. So when this Institution of Engineers was started, so what are the functions of Institution of Engineers? So those things I want to share with you. So the Institution of Engineers, normally we call it as IEI, is the largest multidisciplinary professional body of engineers established in the year 1920. So this institution has crossed 100 years now. It was the headquarters is in Calcutta and incorporated under Royal Charter on 9 September 1935 by the then His Majesty of King George V. The Royal Charter endowed the institution with the responsibility to promote the advancement of engineering among its members and persons attached to the institution. After independence, the institution is a body corporate protected under Article 372 of the Constitution of India. The Institution of Engineers India is administered by the President of India. The institution has been serving the engineering fraternity for over a century with its national and international presence among 31 state centers and 124 local centers. So ours is also one such local center spread all over India. Also it is having 6 overseas chapters. The institution encompasses 15 engineering disciplines with a corporate membership of over 2 lakh members are there all over India. IEA has been recognized as scientific and industrial research organization by the Ministry of Science and Technology, Government of India, and besides conducting its own research, it provides also granting aid to UG and PG students for carrying out the projects. IEA also recognizes the contribution of outstanding engineers and confer annual awards. Some of the awards initiated by IEA are the SAIL Award, IEA Young Engineer Award, Merit Award, IEA Industry Excellence Award, Engineering Education Excellence Award, Lifetime Achievement Award, Best Entrepreneur Award, etc. IEA is the first professional body to represent India in several international bodies such as the World Mining Congress, the World Federation of Engineering Organization, the Commonwealth Engineers Council, etc. IEA holds the International Professional Engineers Register for India under the Global International Professional Engineers Alliance. And IEA also conducts the examinations of Institution of Engineers, namely Section A and Section B, which is equal to B.Tech degree. And this has been recognized by the Union Public Service Commission for the purpose of employment. There are 15, as I was telling, there are 15 engineering disciplines under this Institution of Engineers, namely aerospace, agriculture, architectural, chemical, civil, computer, electrical, electronics, telecommunication, environmental, marine, mechanical, metallurgy, materials, mining, production and textile engineering. And the Institution of Engineers is offering different memberships to the stakeholders. So there are 2 types of membership. One is a corporate membership, another is a non-corporate. So the corporate members, the students who, if you complete your B.Tech, so you can become a corporate member. So under corporate members, they award 3 types of membership, namely AMIE, MIE and FIE. So depending on your qualification experiences, such membership will be awarded to you. And as a student, so you are all student, as a student, you can be a student member. So I think all of you know that our universities are also having a student chapter of Institution of Engineers in some of the departments, and they are also conducting number of programs regularly. And for non-corporate member, again the student chapter can be started, and the benefits for the student chapters are you have the opportunity to participate in the technical events, seminars, symposia, conventions, workshop, etc. like this seminar also. Then also you can participate in national level technical activities and national convention, and access to library facilities at state center. So for Institution of Engineers has got state headquarters in Chennai. For the entire Tamil Nadu, the headquarters in Chennai. So where they conduct regular activities, events. For such programs also student members can participate, and they have a very good library. So you can also refer the library books also. So these are the benefits of becoming a student member of the Institution of Engineers. And ever since its inception, IEA has been the forerunner in setting up national standard for promoting the country's industrial base, which culminated on the formation of the ISI, now called as Bureau of Indian Standards. The state local centers of IEA spread across the country do organize technical activities such as seminars, webinars, workshops, conventions, and provide platform to the stakeholders. So for further details, always you can browse www.ieindia.org for more details. So once again, I welcome our guest today, and also he is going to give a very good presentation on semiconductors and also about the medical devices. And in India nowadays we are self-sustained, and we are able to manufacture the semiconductor devices in India. Earlier we were importing from other US and other countries. So today we are manufacturing, and there is a heavy demand for semiconductor engineers. So all those things will be shared with you by our guest today. Thank you.
Thank you, sir, for the related insights about IEIndia. I now request Dr. V. Siriraj, MIE, Honorable Secretary, IEI TVLC, to share the objectives and relevance of today's event.
Most respected, the chief guest of the day, Mr. Christopher Dandraj, former HCL Vice President working for this chip industry, Dr. Ganesan, our joint extra, CDC, Curriculum Development Center, Dr. Sendil sir, our ISO coordinator, Dr. Anthony, Professor, Computer Science, faculty friends, and beloved students. Today, this session is arranged, I won't say hurriedly, but rather it is a very, very important session. The reason behind this, our Prime Minister is frequently using a buzzword. Can anybody repeat it? Yeah, made in India. Atmanirbhar. So sir has correctly said Atmanirbhar. Okay, now, can anybody tell, are we manufacturing the integrated circuits in our country? In any form of integrated circuits. Even in our laboratory also, we are using AND gate, OR gate, NOT gate. Understand? Then some of the CPUs, all these things, our mobile has got clear CPU, and then our laptop has got, desktop has got CPU, clear. We are not manufacturing anything there. Not even the components are also manufactured. Clear. So, roughly, our country is importing around $30 to $60 billion every year, clear, on these semiconductor devices. So that's why, clear, the government of India has come out with many schemes to make our country as China plus one. What is China plus one? What is China plus one? See, Chinese and Taiwanese are the number one in chip manufacturing. Here, very recently, after the COVID, there was a very, very heavy demand for semiconductor, IC chips. Here, most of our Indian car manufacturers were affected because of this non-availability of the control system chips. Here, right now, all of you are aware that all our automobiles are controlled only by the sensor-based integrated circuits, clear, the ADAS, clear, and then lot of sensor. High-end, activities are happening there in the automobile. So not only in automobile also, in the communication system side also, like the 5G technology, all these things are clear. So where we are importing up to $60 billion, which is a huge expenditure next to our energy import. Clear, the petrol and then the diesel, what we import also. So this has to be eradicated. So that's why Government of India has come out with a scheme of rupees 76,000 crore, clear, as an investment, where here 50% of that money can be given as clear loan with limited interest for promoting the fabrication facilities, fab, clear, that's what, clear, the fabrication facility, clear, but India do not have not even one fab, am I correct, sir? India do not have not even one fabrication facility, but wherein even one fabrication facility needs around $1 to $3 billion of investment. So this is the status of the fabrication, clear, but it is not happening there. But on the other way, if you see our country, clear, most of the chip designs are happening there in India. Chip design. Mind it, sir is also in the same domain.
chip, VLSI, where validation, again it is happening there in India. Sir has headed that particular division also. Clear. So all the basic foundations are done in our country, because if you see, if you go to Bangalore, all the key manufacturers like Qualcomm, they have a center over there. Intel, they have a design center over there. AMD has a design center over there. And then Broadcom. So like that, all these companies have the design center over there in our country. They are extracting all the brain of our India. But as far as fabrication is concerned, it goes on to other countries like China, Taiwan, USA. From where we are looking for our resources with respect to semiconductor. So that's why the government of India, they wanted to establish many such fabrication facilities across our country. So very recently, if you Google it, probably you can see a microphone. There is one company from, I don't know what is the origin of the company, so I may be knowing it, but they are ready to invest around $30 billion. And then the Tata Group has signed an MOU with the Power Chip, that I think there is a Taiwanese company, where they are also going to invest around 20 to 30 billion dollars. Clear. So like that, clear. Many such developments are going to happen there, but in most of these developments, clear, are going to happen in Gujarat, in UP, and then in Tamil Nadu, and then the Karnataka. Clear. So we are going to have that particular edge. That is, the wave is going to come. So if we are prepared to ride in that wave, I think you know how the surfers, have you heard about the surfer who surf on the sea tide? Have you seen it or not? How elegantly the surfer they take the advantage of the sea tide. Understand or not? The same thing that actually we have to do it with proper skilling in that particular domain. What are the scopes available there? Clear. Which are the domain specific knowledge that we are supposed to have? Clear. So if we have that particular capacity, and then the government is ready to provide such a huge funds for these companies, so we need to right now look for skilled engineers in this particular domain. So if we are clear, enabled with those skills, in the coming days, when you pass out or when you search for the peak of your career, so definitely by the time this industry would have come to take you to the heights. Clear. So this is the advantage of this particular semiconductor industry and its ecosystem. So that's why we have arranged such a wonderful, very important topic for today's clear technical talk. Let me thank Christopher sir for accepting our invite. Clear. Day before yesterday only, I talked to him, sir. So we are sitting many times, but that message is not reaching the students community. So that's why I requested him. So he readily accepted. We have to be thankful to Christopher sir for this particular valuable service of transforming the knowledge what he has earned through over 30 years of his tenure to us. Clear? So once again, I thank the students, members of our university, and then some of the students have come from other institutions also. So I wish all of you will make use of this opportunity and come up in flying colors in your semiconductor professional career. Thanks a lot.
Thank you, sir, for highlighting the importance of today's technical session. To introduce a distinguished speaker for the evening, I invite Mr. Amudanandam K, Assistant Professor, ECE Department, Dr. MGR University.
Good evening to one and all present here. It's a great honor to introduce the chief guest for today's session, our 46th technical lecture organized by the Institution of Engineers India in association with Dr. MGR Education and Research Institute. Our chief guest is seasoned engineering leader and consultant with more than 27 years of experience at the forefront of advanced technology sectors. His expertise spans SCADA systems, semiconductor manufacturing, medical devices, and embedded applications, contributing to impactful solutions worldwide. He has played a pivotal role in areas such as wafer inspection, automated test equipment, SCCs and GEM protocols, and large-scale multidisciplinary program management. With professional experience across India, the United States, Europe, and Asia, he brings a global perspective and a reputation for successful bridging between R&D operations and business strategy. His career reflects a deep commitment to innovation, technical excellence, and leadership within a global engineering teams. Today, we are privileged to gain insights from Mr. Christopher Dhanraj on the semiconductor manufacturing process and testing ecosystem, a topic critical to the future of electronics and advanced manufacturing innovation. We are honored to have such an accomplishment expert with us in the evening. Thank you. Welcome, sir.
Thank you, sir, for the thoughtful introduction. And I request Dr. K. Senthil Kumar, ex-officio, IEI TVLC, to felicitate our esteemed speaker, Mr. Christopher Dhanraj. Thank you, sir. The time has come to hear from our expert. We are pleased to welcome Mr. Christopher Dhanraj to deliver his lecture on semiconductor manufacturing process and testing ecosystem. Sir, please.
First, I would like to thank Mr. Vilas. Hello. Yeah. First, I would like to thank Srilra sir and other eminent leaders to providing me this opportunity to talk in front of this learned leaders as well as the student community. Thank you. Thank you. Good evening, everyone. Let me professionally introduce myself with very few words. So, I have roughly about 27 years experience in this industry, and I have been working with many semiconductor OEMs. To name a few, I can say KLA, Teradyne, Advantest, Axelis, Nikon, and a few others. So, this is about me. So, here we are going to talk about predominantly domain. We have been studying a lot in colleges, curriculum and everything. So I am going to provide an industry focus. So how a fabrication environment is there, how a fab is there, and how it is operated, how multiple OEMs, multiple companies bring in their products, how it is interoperating among themselves, how a host system, and how the entire fab is managed in a very high level. Okay, so let us start with what is a fab. Sir has touched upon this fab. Fab is a very specialized factory, and it will be having a lot of different process equipments, different high-tech equipments that will be working in a very controlled environment. Control means, temperature control, humidity control, vibration control, ESD control, and particle control, product control is there. So it's a place, where you will start with, your raw wafer. How many of you know wafer? Wafer. Have you heard about wafer? Okay, great. So wafer is, it is starting from crystal growth, and it will be ignited, will be grown, then it will be cutted and polished, and it will become a wafer. Okay. So here is a place where your raw wafer goes in, and it will go through multiple processes and multiple equipments. Finally, a microchip or nanochip or IC that will come out of this pack. So it's a specialized pack. Okay. So fab environment. So fab environment is very, very critical. This is one of the very key differentiator from any other manufacturing facility. For example, this clean rooms are available in pharmaceutical industry also, but this is very, very different than clean rooms of pharmaceutical industry. So this any fab has to be following the ISO standards from class 1 to 5 process areas. So as Sir said, this is airborne particle temperature, humidity, vibration, electromagnetic interference, everything has to be controlled. So if you take, if you look at this, these people are wearing a bunny dress, and class, it has to be completely covered. So every fab will be having multiple clean rooms. Multiple clean rooms will be having multiple standards. For example, if you take a lithographic clean room, it has to follow ISO class 1 standards. If it is a CVD or PVD, it has to follow different standards. So a fab is a facility where you will be having multiple clean rooms aligned with the different set of ISO standards categorization, and a wafer will be going through all this and it travel across, finally a chip will come out. Okay, so this is the environment. Okay, so why clean rooms? Okay, so because creating a fab, it is a multi-billion-dollar industry. So why we have to have a clean room? What it achieves and how it helps. Okay. Here, if you take, nowadays 2 nanometer chips has come. 2 nanometer chips means it's the very latest in the industry. So 2 nanometer means how small the particle. You can see that. For example, what are all the things that can cause this nanometer chip go for a toss is whatever I have said. The main thing is airborne particles. Airborne particles that can come from human skin flakes, human hair. If you sneeze, the droplet particles, all these things can, fall on a wafer and it can spoil that. For example, if you are working on lithography machine and you are having a light source coming in and it has to go through, if your hair falls on that lithography, your entire wiring will go for a toss. Okay, so that's the one, that's why it has to be a very clean room. So for comparison, if you take class 1 clean room like a lithography, what will happen is, the particle count and the particle size has to be very much limited. So here, if you look at this 0.1 micrometer and 10 micrometer, the particle size has to be between this. To give a reference, if you take your hair, its diameter is about 50 to 60 micrometer. So you can compare yourself how thin, how the particle has to be. So particle count means if you take a cubic meter area in any one of the clean room, if you take that 1 cubic meter, if you take that within that 1 cubic meter, what is the number of particles and what is the size of the particles that matters. That's the reason every clean room will be having a particle counter. So the particle counter, for example, if it is a class 1 clean room, if it goes beyond certain number and if it goes beyond certain size, what will happen to generate alarm? Immediately this has to be investigated and the production has to come take halt. So that's why you need to have a very clean room. That's why you need to enter in a very clean, you need to sanitize yourself, you need to enter inside. That's why all these people will be wearing a bunny suits to minimize this contamination. So how we can minimize the contamination? So one is, for example, the lithography areas, That's where you will have that, class 1 clean room, where you need to change this, the shoe cover couple of times. First you need to change, then you need to you need to enter into a new area, second stage, then you need to change your cover, then you need to walk through the sticky mats. The sticky mats will capture all the, particle underneath your shoe cover, and they need to go. And this one is a air blower, and it's not shown very clearly. So the air blower that will blow air. So these are all the air blowers. When you actually go in actual fab air blower, you will be going through the zigzag path. So that when you are traveling every direction, it will blow air. So that all of your dress will be air blown, and you will be entering into the fab. So that the contamination due to the external particle that will be removed. If you look at this previous slide here. Here, the temperature, particle, temperature, humidity, vibration, electromagnetic interference, these are all non-human interference. It will be controlled by machine. Whereas this airborne particle, and this is only human interference, it will be having all contamination. That's the reason these are all the precursor steps are taken. So if you look at the fab, this is how a typical lab will look. If you open the door, if you go in, this is how it will look. This is how it will look like. So here, this is a cassette stage. This is where you will be having this called the cassette, where you will be having a lot of wafers. And this is one machine. Let us assume it is a wafer inspection station. This wafer inspection station will take this wafer from this cassette. Look at this. This is a robotic arm, and it is having a wafer catcher. Wafer catcher, it is nothing but a vacuum thing that will take the wafer and it will put it in. So that's how this machine is placed. So this is the cassette, and if you look at this one, this is called the cassette port. So this cassette will be traveling in this port across the sphere. So what happens is, so if one wafer per day, it will be traveling roughly about 10 to 15 kilometers on one day, depending upon the complexity of the wafer. So you would have noticed one thing here. So if you look at, there are no people around here. Did you notice? Yeah. So the reason is the people will be getting into this fab only as and when there is a need. Without any need, they don't want to introduce any contamination into the room. That's the reason this is almost empty. So there will be a path light system. If you look at this, this is what is a path light system. So this is red, yellow, green. This light will be there. So this will be communicating the message outside. If you look at from the outside, this is how you will look at this. So look at this path light. So this is what is a path light. So this path light communicates. If it blinks, it is a meaning. If two combinated lights blinks, it's a different meaning. So this is how clean room equipments will communicate the message to the others. That's one way. Okay, for the fab managers. So all these floors are maintained in a electrostatically protected one, and this is a stage 1, and this is the process 1 will be completed here. Then the cassette will be going here, and it will go get into this, and the second process will start. So the third process, so it will go on, and it will be traveling through this. Okay. So now you are seeing a lot of machines, a lot of equipments, and a lot of timing. For example, this is machine A. It is completing a wafer inspection. The wafer inspection station completes the wafer. Then it has to communicate to the next machine. And this has to say this wafer, this cassette, all the wafers are scanned and detected for any errors. Then it has to transmit this particular cassette to the next machine. So there should be a communication and control between these two systems. So this is how the entire system will be communicated and controlled by a MES system. That's what is the picture here. If you look at this, this is our manufacturing execution system. The manufacturing execution system has EAP. EAP is nothing but equipment automation program. So this equipment automation program, it's a hub. For example, this will talk to this SECS GEM is a protocol. Semiconductor communication system and the generic equipment model. This is what is the protocol. Through this protocol, this EAP controls deposition, lithography, etching machines, cleaning, packaging, all these things will be controlled by this EAP system. Whereas MES controls this. So this is how each machine talk to each other and communicating and controlling the stuff within themselves. Okay. So here, this is one of the wafer inspection station, and this is a robotic arm. This is manufactured by another one equipment manufacturer. This one is created by another equipment manufacturer. These two has to sync among themselves. It has to interoperate among themselves such a way that it will be a task can be completed. How this is done? This is again done by the common standards and the CCFGM protocol. What happens here is this robotic arm takes and puts the cassette here first. This is called alignment model. This is a wafer inspection alignment model. This alignment model will do a wafer alignments. And once the wafer alignment is done, then it moves the cassette from here for wafer inspection. Okay. How many of you have seen a wafer picture? Okay, so most of you have seen. Then I will show you what is a wafer. Okay, so typically here, see, a single wafer per day it travels between 5 to 20 kilometers. If it is a simple process, comparatively simply complex, it means it will travel minimum 5 kilometers. If it is a very complex, like 20 layer, 30 layer wafers, it has to travel roughly about 20 kilometers per day. Okay, depending upon the complexity. To complete from a wafer to a chip, if it is very complex, it travels roughly about 200 to 300 kilometers. Just you can imagine how complex the system, how complex the protocol, how it is interoperating many things. So if you look at, if you take deposition lithography, each is its own industry. Deposition its own industry, it has its own manufacturers. And lithography, they are having the 4 or 5 manufacturers. So like this. All these different companies, different equipments, how they are interoperating is through this fab automation. Okay. Okay. So this is a typical, fabrication steps in a 10,000 feet view. 10,000 feet view is big picture. So it doesn't cover everything. I'm capturing very, very important one. Okay. So here, this is what is a wafer is. So this is what the wafer is. Here I could simply start because for the real estate issue beginning this particular slide. So the next thing here, this is what is a wafer preparation. So first what happens, a crystal grows. Once a crystal grows, it grows like this. This is called the inert or what. So it is cut into multiple things. Then a wafer shaft cut into a small tiny wafers. Usually it will be 200 mm wafer or 300 mm wafers. So 200 mm, 300 mm is its diameter of the wafer. Okay. Once it is cut, its edges polished, then it will be printed with the laser mark. So it's for unique identification of each and every wafer. So this V mark is primarily for a reference point. For example, if a wafer doesn't have this V mark, what happens? It is 100% circle means there should be a reference mark. With that reference mark, it can identify a particular location into X and Y coordinates. Without this reference mark, it is very difficult to, you cannot make it. That's why it's called marks. Then wafer lapping mix, which is shiny wafer will be grinded. Then it goes to multiple testing process. Finally, the wafers, these wafers are loaded into 20 wafers will be loaded into the cassette. This is called a shiny wafer gesture. Okay. So now a shiny wafer comes here, it goes to oxidation process, then photolithography, we call litho, and this is etching, then this is ion implantation, this is metal, it's called wiring, it's called metal deposition technically, then it will go for chemical mechanical polishing, then it goes for energy density spectroscopy. This is where you will be identifying a lot of defects and all that, and then it will go for dicing. Dicing means once the wafer, this is what is a pattern wafer. Pattern wafer, if you look at this, there are multiple chips embedded into this. So once this process is completed, you need to cut down all these chips into a small die. So this wafer will be cut into this small die. So this dicing itself is interesting because there is a shaw cutting, there is a laser cutting, and there are multiple types of testing, and multiple companies are working on this, and multiple products are there for each and everything you rather say. Okay. Then the die is attached with package prostate. Then once it is placed, then there is a wire bonding. The wire bonding is a very big industry. Wire bonding can be done with gold wire, silver wire, tungsten wire, depending upon the complexity of the chip. So once the wire bonding is done, then it will be encapsulated, and this is what you see as a chip outside. So the chip will undergo a lot of tests. Not only the testing is happening in the ESD space, and the testing will be happening in this space as well. So once this is called this end product, which is nothing but a chip. After this, the chip will be a complex chip. For example, if you take your mobile chip, the mobile chip is a mixed signal. Mixed signal chip. Yes. So you will have analog, you will have digital component, you have a lot of it's a mini computer, right? Nowadays, your latest mobile phones are mini computer. So those computer has to be tested. So how will you test? Yes, it is SOC, system on chip. So system on chip means you have a analog portion, a transmitter, a receiver, a DRAM, a memory, internal memory. So many things are there. How will you test it? You need to test it each one by one. So if you want to test a DRAM, there is a separate testing mechanism and a testing module, testing equipment to test only the memories. Then if you want to check, analog digital A to D converter, and A to D converter means your analog. For example, now I am speaking, the voice is creating analog wave. This analog wave is digitized, and it goes and it receives the speaker, and that's why your mobile also is similar. So how will you do that? So you need to have an A to D converter. So your analog voice, and what happens during the testing? How will you generate analog wave? So there will be arbitrary waveform generator that will generate the waveforms. Then that will be digitized. Then it will be sent. Then the digitized waveform will be again converted back to analog. That's called a D2A process, digital to analog process. Then it will be hearing in the mobile. So all this has to be tested separately. So that is not post end product testing. Okay, that's a completely different ballgame. That is covered in one thing, but it is very big system. Okay, so now let us go one by one as a overview. Okay. If you take TSMC, that is a very big one, Taiwan Semiconductor. TSMC that spans around hundreds of acres. So there are multiple fabs. The capacity of that depends on the complexity of the devices, because you will be having, if you are taking this particular machine, in your fab they have a number of machines, and lithography is again a number of machines. So depending upon that's called capacity planning. Every fab, if you are giving order for 5 million chips of particular type, for example, you have PlayStation 4 chip you want to give order. So what happens is they will take that order, they will do the capacity planning. Once the capacity planning is done, they will calculate the throughput. Once the throughput is calculated, then they will tell you, they will put some buffer and they will tell you this many times. So it is a complete planning exercise. For example, once the end product is created, to test that you need to develop a lot of things. For example, if you want to test an end product chip, you need to develop a device interface board. That itself is a big time-consuming process, because if I am a Samsung, I'm creating a new mobile chip or anything, then I will provide my specifications, my data sheets to them. The field engineers will work together and they will come up with a testing mechanism, test management. That itself is a big thing. So it will be totally depending upon what is the complexity of chips, how many machines you are going to utilize on this, how many cycles you are going to go through this cycle. Based on that, a plan, and based on that, the throughput will be and the output will be planned. Okay. So, okay, so this we are covered. So here I put just one start, but this is what the entire thing happens before that particular start. Okay. So now we go to. Oh, this is some snapshot of what Dr. Srindra said. So these are all the process steps. These are all the OEMs and what company and which country they belong to. So this will give you a glimpse. For example, the wafer preparation, Samco, Siltronic, Global Wafers, Disco. These are all the companies are involved in wafer preparation. Wafer preparation is creating a shiny wafer, which is nothing but this one. For this one particular process, these many companies are there. And if you take oxidation, thermal and annihilation, these are all the companies. TEL, Matson, Applied AMD, these are all the companies. These are very top players I have put in. There are many companies in China also that I have not captured for the amount of space. Then lithography. ASML is the market leader in lithography. Nikon, Canon and Microtech, PVG, these are all other companies. So this guy is the key player. For etching, you have Lam Research. Lam Research is in Bangalore, and TEL is in Bangalore. AMD is also in Bangalore. So many companies are in India. And if you notice what Srindra said, government is investing heavily on this semiconductor. They have a plan like 2030 plan. They already initiated 2024. Government is giving a subsidy of roughly about 72,000 crore. And 5 companies have been shortlisted for this program, and they are totally investing 1.52 lakh crore. It is a very big money. And the Electronics Association, the Electronic Skill Development Association, they have highlighted there is going to be they are going to create roughly 1 million jobs in 2026 alone. 1 million jobs means 10 lakh people, 10 lakh qualified people. So this is going to grow, and it's not going to come down in near future. So this will give you, it's just to give you a glimpse of, how many companies are there. All these people are going to come down here either directly or they will be having a subsidy. If you take ASML, Nikon, Canon and all, these people, they are using a laser, sophisticated laser, that is a company produces China. So if you take ASML, they are working with hundreds of companies, slightly Nikon also and Canon also. So you need to have a lot of ancillary industries going to grow apart from semiconductor major thing. Lot of small companies, lot of equipment suppliers, subpart suppliers. So many people are going to come into picture, and all those people need people. So congratulations to all of you. You are in the right time. I will travel say. So this is for Axitron. Most of the companies, HCL, we have been working with many of these companies. So these are all, just a glimpse of, what are the opportunities, what are the companies, what are the areas, these companies are there, and what is going to, you can see the future again. Okay, that's right. Now we will take this, first one, oxidation, and we will see, what is this oxidation. I will give you only a brief view of, what it is and what process it's going to take. For example, here this oxidation is nothing but it's creating insulated layer, because you got a shiny wafer and you need to insulate, because yes. No, connection here. This one is the question is for everyone. The question is each box will be having a separate message. Yes. For example, in oxidation, there will be at least 2-3 companies will be working on that. There will be 2-3 platforms of messages will be available. Same with the photolithography. Okay? Well, you can choose between, for example, here I have said. Yes. So for photolithography, ASML is a market leader, is one company. So if I am Intel, I want to do a photolithography, I want to create a chip. So I want to create photolithography, means I can go and buy equipment with this ASML. Yes, depending upon the chip and the complexity of the chip. And Nikon, Canon. See, you have noticed Nikon and Canon, these are all, glass companies, lens companies. Because of the photolithography, these people are, they are in the picture. Okay? So, no. That is one of the, Because the ASML one machine cost you on the nano scale, it is going to cost you multi-million-dollar. Okay, it requires a lot of tech. See, I visited this facility because there are a lot of constraints being overcome by government. For example, in Nikon, I visited this place. They don't want us to bring certain things to India because those technologies are military grade. Okay, so there are the governments, multiple governments are working together. The China Plus One, what Sir said this, it's one of the initiative. So these things are getting eased. Okay. Do I answer the question? Okay. So this is electrical. See, you want to create electrical isolation. For example, you are creating a wafer. The wafer has to be electrically isolated. Then only you can print a die, which is nothing but your transistor, FET, MOSFET, all those things can be printed on top. So this is a basic isolation layer. What happens here is, this is what is a feeder, we used to call it feeder. Here you will put a quartz board. The quartz board will be having a slots where you will put all these wafers and it will be closing this. And this is a heating coil. This will be depending upon the size of the wafer and the nature of the wafer. It will be heated from 800 to 1200 degrees centigrade. It will be heated. When it is heated, either sodium oxide, nitrous oxide or silicon oxide or different gases will be sent into this. It will go immediately, it will get expanded, all these ions will be equally deposited on that and it will become isolated. So this is done by a machine. This is why it's just a diagram. It is done in a very controlled environment because it's a very high temperature and the gases will be sophisticated and this is done with I haven't put that machine. Okay. Once this the second process is are with the litho. So what is the graphy? Here what happens is, so this is what is your wafer. In the oxidation, this is what you have done. This is called oxide coating or oxide film, which is nothing but an insulator. The third thing what you will do is, you will do that photoresist. The photoresist material is, placed here. So this is what is the photoresist material. And if you look at that, this is what is it's called mask. Some people call it a reticle. So this reticle is the one, it will be created as this is what is going to be printed as a die. For example, some of you would have used cadence software in EDA. Heard about this? Okay. So EDA cadence software will be there. The cadence, same cadence, you can convert this, the chip cadence of the output into this lithography output. So this will be, this reticle will be nothing but these are all opaque area and this is all transparent area where UV light can pass through. So this is opaque as well as the pass through area. This is what is called the reticle. For example, if you are having a 5-layer chip. So first layer, one reticle will be there. Second layer, there will be another reticle. So 5-layer means 5 reticle will be there. Okay. So this reticle is placed here. The reticle has to be aligned with the wafer. If you recall, the wafer will be having a V-cut. So through the V-cut, they will be aligned and it will be positioned in one particular direction. Once this reticle is placed, the reticle and the wafer will be aligned. So the light source will come in. This is called the UV light. The UV light will, first it will place here. The die will be printed here. This is called the pattern. Once it's printed, it's called the pattern. So this pattern will be printed here. If you look at this lens is a very expensive, very sophisticated lens. So because of this lens only Nikon, Canon are coming into lithography projects. So this lens, what happens is the UV light will be converged to a nano scale. So how deep, how sharp you are converting, the size of the chip is going to be that small. Got it? So the lambda of this UV light plus this lens is very important. So first what happens is this light, the reticle is there, this will be there, these two are constant. This is placed in a chuck. Chuck means it is a table, round table. It can go X direction, Y direction, this direction. So what happens? First you are printing the lithography in this particular chip. Then you are moving your chuck moves to the second chip. You are printing here. So the chuck moves in X and Y direction, and all these things are getting printed here. Okay. So that's what captured here. This is nothing but a photoresist. On top of photoresist material, you are masking. and you are passing the UV light. The UV light is creating a chemical change into that photoresist area. The chemical change is going to be very useful. We will capture in the next covered slides. Any questions? I will keep on moving. Okay, just keep all your questions. Probably end of this session we will give a Q&A. Okay, so here you are seeing a wafer from the top. Here you are seeing a wafer horizontally. So this is what is basic silicon. So this is what your insulation layer through oxidation you have done. This is a polysilicon layer. This I have, because I have not covered all the key steps. So we are jumping from here to photoresist. The photoresist, because this is what is the exposure. The UV light exposure has happened. Once it is exposed, this area has to be etched out. Etching is a process. Etching is a separate machine. So it is a separate process. It removes material from the predefined selective areas. So this is what's created with the lithography. Here you are etching it out, and this is what is the cavity it is created. This is called the VR. VR is connecting one layer, or probably you can keep your transistors or FET or MOSFET, whatever you want to create, that will come together. Okay. So that's why in the transistors, interconnect or vias, anything can be created through this process, this etching process. So here your photoresist, here you are etching out, you are creating cavity. Okay. So etching, there are multiple things, wet etching, plasma etching, so many things are there. I am not putting everything here because for want of time. Okay. So we take simple wet etching area. Means the wafer will be go through a chemical solution. It will be dipped into that. Then it will be again washed with the deionized water. Then all the impurities in that, everything will be going out and it will be creating a cavity. Yes. Chemical wash, then deionized water wash. So the next is doping. So it's called implant, doping implant. So this is what is a doping machine. What happens is this is what is a doping donor. It can be depending upon N type or P type. You will be either put boron, phosphorus, arsenic, or whatever you want to implant. Those ions will be going here. And this is what is a wafer. The wafer will be vertically placed in here. Here, what happens like, CRO, electron beam kind of thing. So this ions will be shooted out and it will go through this, and there are cathode, anode and magnetic things, so that it will rightly go and scan the wafer like this. Scan and it fills this. So what happens is, this is a very sophisticated thing. Okay, the reason is you need to pump the electron with the right speed and the right direction, and the ion has to penetrate only to the certain depth. And another complexity is the number of for count, say you can take, assume you are doping with 50 ions. So the 50 ions has to travel in the right speed, and it has to embed only within this region, and the number of ions also has to be same between all wafers. So that's the reason it has to be uniform, and the entire doping profile has to be reproducible. The reason is, otherwise what happens? If any one of this goes wrong, what happens? Either the doping can go deep inside, or the number of ions can be more in one chip and less in another chip. You understand the point? Or the ion can damage. So finally it will become error. Okay. So that's why this implantation process is again sophisticated. So this is what the ion beam travels. It is deflected and it is using this electrodes, anode and cathode and the magnetic things. It will be pointing the right area and it will be doping the right wafer and the right place. So this is how this area will be doped. This area will be doped. Either N type or P type. So once the implantation is done, then you need to wire that. So metal deposition comes into picture as the next thing. So this is what is your wafer. So you dope this with the implant in here. So what is next? So this is what your either aluminium or gold or tungsten. or silver can be used as a metal deposit. This is nothing but a connector. So you've done all this, then now you are wiring it simply. Okay. So this is what is called metal deposit. Okay. So now you have created one layer. Wafer is there. You have created photolithography. You have done etching, and then you implanted. Now you are wired. Okay. Any questions? Okay. So the next thing is, now the moment you are wiring this, the aluminum coating will be, there will be a lot of ups and downs. A small cavity will be there, and aluminum deposit particles, micro particles will be falling on the wafer. So what you need to do is you need to clean it, and you need to polish it, and you need to make it a next level, so that next layer will be placed on top of that. So what happens is here, this is what is your wafer is, and this is what is a spindle one, base spindle, and this is another spindle, pneumatic cylinder spindle, and this is what is a pad, polishing pad. This will be rotating, the wafer will be polished. Extra metal will be removed. This is slurry dispenser is a specific mixture. It will be washing this out of all impurities, and once this chemical mechanical polishing is done, it will be polished. Then a dielectric coating will be done. It will be ready for the next layer of wafer deposit. Got it? So this is a multi-layer question. For example, if you look at here, after this polishing, it needs to do a testing, wafer testing. Then it has to go to dicing. If it is a multi-layered one, this process will be repeated until you are meeting the number of layers.
So recently, how many layers are being stuck?
It can go up to 30 layers. Intel chips, sophisticated chips, and all goes for up to 20 to 30 layers depending upon the complexity of the chips. Huh? Depends. For example, you can build a 50-story building, you can also build a 100-story building. Depends upon. So you will be preparing the wafers and say whether how many buildings you want, how many layers you want to go. So this is what happens. First deposition, then coating, then lithography, etching, ion implantation, then cleaning, chemical mechanical polishing, then dielectric layer deposit again. So the cycle goes until you can look like a multi-story building. If it is a 50 layer means 50 floor, you can think of its analogy. Okay, so that's what you can think of. Okay. So what are all the defects a wafer can have after completing this? This is what happens in the EDS. We look at this. See, this is the EDS. Energy density spectroscopy. In this spectroscopy, these are all the defects are identified. So, defects will be identified by where means in XY coordinates in which area. Then what is the size of the defect and what is the composition of the defect. These are all defines a defect. For example, in the metal deposit, you rupture the wafer or there is a small cavity or something. This is called a topological defect. And your skin flakes and your hair or something falls on here, these are all particles. These particles are called contaminations. And if you look at this organic layer, inorganic layer, organic layer means carbon based particle and inorganic means non-carbon based particles. So dust, carbon dust or non-organic dust. If this is being placed here, this is called molecular defect. And this is an atom. For example, we saw that doping, ion deposition. If you deposit more ions, what will happen? It will create problems in lot of other things. Your electrical characterization, electronic characterization will change. So this is called atomic defects. So these are all contamination. So these are all called category of defects. These are types of defects. So these are all the things are done in the EDS. Okay. So the EDS a little bit we will deep dive. Okay, because this is the one will be used. Why I want to do this is because in each process this EDS will be used. Each cycle EDS will be used. Okay. Okay. So this is defect. Yeah. First samples will be taken, sample wafers will be taken, and it will be programmed. One cassette will be, one lot will be taken. It will go through, all the wafers will be go through the CDS process. So the types of defect, categories of the defects will be identified. So how many number of defects, for example, you can say a defect particle of size 10 micron, immediately the particle counter has to be blamed. So lot of debugging will be done in this process. No. Error is found, a sample wafer will be sacrificed. So the learning out of this will be implemented, then it will go for production. So this one defect, there are a lot of defect detection technology, dark field optics, bright field optics, a lot of things are there. Here we are taking one optical based one. So this optical based one, these are all the light source. This emits light into the wafer. This was sample wafer, it emits the light. The light is reflected back to the charge device and CMOS defect. This is digitizing this entire wafer as a picture. Then this picture goes to image computer. This itself is a technology. This itself is very sophisticated. It's not a simple image processing technology. There is a final level board. So many boards will be there. So it will be comparing and it will be calculating the intensity of each and every point. And if it finds intensity difference beyond certain point to certain point, it will treat that as a particular defect. So this is how this technology works. So this is what is bright field optics. Understand? You are with me all? Okay. So SEM is scanning electron microscope that I will show you. This is a SEM test. So here the E-beam, we used to call it E-beam inspection. E-beam, there is some term will be there. This electron beam, the electron beam will be shooted onto the wafer. So what happens is here, it travels through anode, cathode and a condensing lens, finally it will be focusing on this. So this is a scan generator. So the scan, this is called the scanning beam. This is a reflection beam, this is a scattering beam. So here E-beam, electron beam is here. This is a photo detector, electron collector. This one is X-ray detector. So this will also detect a comparison between the source beam as well as the capture. Everything will be taken into consideration, and this will be used to find out whether the particular point having a defect or not. Okay. So this is a deep dive. This is a point by point. It is very slow, but it will be very accurate. The picture will be very accurate. Whereas in the term I have not captured because term, when you are doing term, as are asked, a particular defect, keep on repeating. We want to identify whether it is a carbon based or not carbon based. We will use term technology, and it will go and it will destroy that particular thing. Out of this, it will figure out what kind of particle, what kind of molecule, what kind of atom it is. So that is transmission electron microscope that I have not captured because a lot of things can be captured, but I don't want to because of amount of time. So once this EDS is done, then it goes to dicing. So dicing, there are multiple technologies are there. Here I have taken only one for the first. It will be the wafer will be mounted on a dicing table. Once dicing table is mounted, there will be a cross section, and you need to align this. Everywhere in the wafer technology, everywhere the alignment is a separate thing and very complex thing, and it is thick. Because if you want to cut it, if a laser is this is laser cutting, when the laser will be pointed at one direction, the entire wafer will be moving XY direction, so that it will be cutting each and every day very accurately. So that is what is happening in this particular table. So it has to be very clean, and it has to be ready for it, and cut, and the cut particle also, the slurry particle, that's what we used to call. It will be also has to be rightly eradicated. So one is alignment, one during the cutting, the slurry particles, how that is going to be eliminated with this laser cutting is the key technology in this particular space. Okay. So once dicing is done, it has become a single die. So if you look at this, see, it has become a die now. So these are all the multiple dies embedded in a wafer, and this has become a single die. Now you need to attach this with either package postage or ceramic or anything can be used. So it will be attached here. Once it is attached, this will be, the points will be wired through wire bonding, then it is encapsulated. Okay, that I have captured in the next. Sorry, I'm taking a little more time. Okay, right? So here, I think we will give it as the last slide. So this is what is your die. So this is what is your die. This is what is repeated instruments. Number millions of transistors, billions of transistors, a lot of MEMS, MOSFET, all. Let us assume it's a CMOS chip. So now you need to wire this particular thing with the legs. So this is a gold wire bonding system. So the gold wires are bonded and this goes to each and every leg. It's a part. So the part means you will have all the four sets you will be having a pin. Wire bonding is done, and once it is done, it will be encapsulated with the chip cover. Then it will be called a complete end product of a particular chip. This also will be taken by, it's called yield. So as sir asked, how your testing is done. First yield will be taken and it will be go for series of testing, qualification testing, alpha testing, beta testing, and all the issues will be found out. Then it will be go for mass manufacturing, like 5 million chips, 6 million chips, or n number of million chips. Okay, so that's how this wire bonding is done. Okay, so we are simply covering. Almost we have covered everything. So this one is a package chip is called. Okay. So apart from this, there are multiple technologies, multiple companies. For example, once it's a packaged chip, Teradyne, Advanced. A lot of companies are there. They are developing automatic test equipments. The automatic test equipments, it's a completely different ballgame. You need to have a device interface board. Then multiple chips will be, the robot will take, you would have seen videos, the robot will take the chip and place in a deep board. Then a lot of power supply leakage test, continuity test, and the differential test, power supply at each point, all these tests will be done on top of that. Okay, so that's a different thing. I'm not going to cover this in this session. Okay, so I think that's all we have covered. And now, any questions we have? We'll go for a Q&A session. Any questions in any of this area? Yeah.
Normally, how many days
It depends. See, if you are going for a very less complex chip, it will be planned. That's called test plan. See, manufacturing plan, test plan are the two different things. So they will be your field engineer. For example, if you are having a lithography, all these engineers, they will be having a meeting with probably Intel or Broadcom or Qualcomm or any company who is going to manufacture the chip. They will be looking for a complete plan, technical information. The technical insights will be discussed among these people along with these experts, and they will come up with a test plan. It will take months. Once the test plan is done, capacity planning will be done. The fab has to be free. Then finally they will take, this can be done so on so time frame, and this is what is the duration. To answer the question in a simpler way, a chip, a less complex chip will travel, a small chip, less complex will travel 5 days, it will travel 5 days within a fab. So depending upon the capacity planning and the number of yield you want, if the yield is about 90% and you want to make 10 million means, 10 million 90% it will go for a waste. Right? It will be going for different purpose. So it will be planned. You cannot say simply for how long a chip will take to come out from raw state to product. It's a complete plan. Any other questions?
Sir, I have finally I'll ask you.
Okay, sir. Yeah, analytics, for example, you are detecting a defects. So, A comes everywhere. For example, this is what is your detection. So, you can train your system to identify. We used to call it all these defects will be clustered. That's a direct clustering means we will say this particular topology, how many clusters are defects. Before, it is one of the examples. You can use everywhere. Wherever you are having a data, wherever you are having a sensor, you can use that, create a data lake, and run analytics. Today, there is no field, everywhere you can use AI. Right? Yeah. As far as I know, we don't have it. Right now, assembly, small assembly units, PCB companies are there. If you are going for a small PCB or something. Yes, sir. Right now, 5 companies are forming a consortium and they are coming up in a fab in Gujarat, Assam. Sir said it during